Swayam Prabha. Digital India. Educated India.
We will begin by looking at some representative examples. The motivation of why we talk about program analysis, we will talk about optimize, and then we will look at a concrete example of a contemporary optimization which optimizes heap memory. So, let us look at classical optimizations. This is textbook stuff. Those of you who have done compiler construction course would be familiar with it. Those of you who have read Aho Setty-Ullman's book would be familiar with this example. This example is from that standard book. There is a standard quicksort routine, and what it does is it sorts an array by taking the indices m and n, the indices between which the values are to be sorted, and what it does is it finds a pivot and then moves the smaller values to the left of the pivot and the larger values to the right of the pivot, and then makes recursive calls to sort the smaller parts of the array, the standard quicksort program. Of course, we are not so much interested in what the program does, we are interested in knowing what a compiler can do with the program. And so, I have highlighted this yellow box. This is a part of the code that we are going to look at. As you can see, it is a pretty complex code. We have some assignments, then there is a while loop. Within that, there are two do while loops and there are array accesses, etc. So, you want to see what a compiler can do given such a reasonably rich program structure. So, this is how the intermediate code corresponding to this yellow box looks like. So, we have I is equal to m minus 1, j is equal to n. Let us look at these first three assignments. So, how do they get represented? I is equal to m minus 1 appears pretty much as it is, j is equal to n, and then the next assignment v is equal to a of n gets translated into T1 is equal to 4 star n. Can someone tell me why this is happening? Why is this T1 equal to 4 star n? Why do not we simply, so we have T6 is equal to a of T1, why are we not doing T6 is equal to a of n, which is what was there in the original program? Beg your pardon? Size of integer is 4, and therefore, we are going, so in memory we are going to look at an array as a linear collection of bytes. Not every compiler would do it this way. For example, if you look at GCC, GCC until a long time retains the array access information as it is without doing address calculation. I mean, until it reaches the expander phase, until it produces the first RTL code, arrays appear as they were in the source program. But this is something that a compiler could do. So, what is happening here is that there are lots of computations that are generated by the compiler, they were not there directly within the program specified by the programmer, but the compiler translates these into some specific ways. So, this is how typically the code would look like, and we can observe some more things. For example, we have this, after these three assignment statements there is a while loop. Where does that while loop appear? So, we have something, nothing that indicates, but somewhere there must be a go to 6. So, this statement number 24 is this, from 5 to 24 is, what is this, do while loop. You would notice certain colors, background colors in this slide. Can you guess what they indicate? Apart from my good mood, what do, I like colorful slides, but memory address calculation. Anyone else? A more precise answer? same computation has been given the same color, right. That is the important point. The important point is that there are many computations of 4 star I here, here, here. There are 2 computations of 4 star n. There are these assignments A5 is equal to A of T4 being multiply done here. 4 star j is being. So, I wanted to highlight the fact that when we take a program and compile it, take it to a slightly lower level of abstraction, it exposes many computations that are done again and again. And the question is, can we do something about it? Do we have to compute 4 star I so many times? Do we have to compute 4 star j so many times? Can we compute them once and for all and store their value and reuse their value? That is the question, and that is how we can optimize a program. Okay. So, this is a typical translation done by a typical compiler that exposes many redundant computations, and any optimizing compiler. So, one of the classical optimizations try to eliminate these redundancies. So, how do they try to eliminate these redundancies? In order to analyze the programs, they create a control flow graph that has basic blocks as nodes. And what are basic blocks? Basic blocks are maximal sequences of linear control flow. There is no control transfer into the basic block except at the first node, and there is no transfer out to the control flow block basic block except at the last node. That is what is a basic block. Later we will see that in the limiting case a basic block could as well be a single statement, but for now let us continue with basic block as a group of statements. So, once we do that, these are how we find out as basic blocks. The algorithm to find basic blocks is very easy, no need to get into too many details. The idea is that any target of a jump instruction begins a new basic block, and then any statement that follows a conditional jump, because the jump could be false, begins a new basic block. Once we know these statements, we can identify the maximal sequences of statements. So, this is how we get basic blocks, and this is how we create a control flow graph out of this intermediate representation. And as you can see, we had this large do while loop, and this large do while loop looks like this. This is the do while loop, and within that there are these two large while loop, and within that there are these two do while loops. So, that is the idea, that is the program that we have. It is not too hard to map this program to the original source code, right. And now we can ask certain questions. Now, why do we want to create this basic block? Because we want to ask a question, is this computation. So, we have let us pick up some computation. We have this 4 star I and we have this 4 star I. So, clearly the program starts from here. So, this is computed first and this is computed later. So, can someone tell me whether this computation of 4 star I is required or is it redundant? What does your intuition say? It is redundant. Why is it redundant? How would one define, okay, we will come to this question later. How would one say that if there is a computation E here and there is another computation E here expression, how will we know that second computation of E is redundant? How do we define that? If it is calculated repeated, I am giving you, this is E and this is E. Okay, I have 4 star I here and I have 4 star I here. Can I always say that this 4 star I is redundant? Value of I is same in a control flow graph, in a control flow path or every path from. So, the value, the idea is the value of variables should not change between the two computations. Okay. Now, can you answer that question? Is there a value changing? Is the value of I changing? Is the value of I changing after this computation? Yes, yes, very good. Now, so is it redundant? Is the second computation redundant? No, how can that be? So, you see everyone starts doing this, that, you know. So, we have to have a systematic method of doing this and that. Okay. Program analysis is exactly a systematic method of doing this and that. Okay. We will see it over 2 days. Okay. So, we want a systematic method of being able to answer this question. So, as a first step, what we do is, because there is control transfer in between, we simplify the problem and say let us not worry about the overall control flow graph, let us worry about a single basic block. Now, the property of a single basic block is there is a strictly linear control flow. So, I can examine a basic block without looking at the surrounding code and I can take some decisions. I do not have to worry about it. That is why the concept of a basic block is very important. So, let us look at this basic block for example. We have 4 star I here and 4 star I here. Now, is this 4 star I redundant? Yes, now we can say it with a reasonable certainty. So, this is the optimization called local common subexpression elimination. It is called local, it is local to a basic block and it is common subexpression elimination. There is a subexpression 4 star I which is common, which means that we are finding repeated occurrences of the expression and the value of the variables between these two occurrences is not changing and therefore, the later occurrence of the expression is redundant. So, all I have to do to perform local common subexpression elimination is to do this right click and local common subexpression is done, elimination is done. So, all these occurrences, so even 4 star j they have been eliminated. Okay. Now, we want to perform global common subexpression elimination. So, global is across the basic blocks. Now, what can you say now? Now that you looked at the issue for a while, is this 4 star I redundant? Yes or no? How many of you say yes? Please raise hands. How many of you think no? Please raise hands. How many of you think? Please raise hands. I should get a complimentary set yes and no. Let's hear from the no camp. Why the answer is no? Any guesses? Every time the value of I is changing in the loop, in the inner loop, right? That is the objection of the no camp. How does the yes camp overrule that objection, if at all?
The last computation might be redundant, but other than that.
Yes, the important point is that when we are talking about two occurrences of an expression, we should talk about the last occurrence of the previous expression and the first occurrence of the last expression, right. So, even if the value of I is changing, 4 star I is once again computed, right, and we are talking about a path that goes from here to here. So, yes, that path might keep taking this loop again and again, but there will be another occurrence of 4 star I, right. So, it is very important to realize that we are talking about execution paths in which the same statement may appear again and again, but when we compare occurrences of statements to different occurrences of statements, we essentially talk about the last occurrence. So, yes, after this 4 star I is modified, after this 4 star I is modified, after this 4 star I is modified, but assuming that after that the control flows from here to here, I is not modified. So, I is not modified and therefore, 4 star I is indeed a redundant computation, right. So, we can perform, so we will see a technique that identifies this automatically without human reasoning. Okay. So, this is what we talk about. So, we can perform global common subexpression elimination, and those occurrences of 4 star I and 4 star j are also gone, right. Let us talk about the next optimization. There are other classical optimizations, copy propagation, strength reduction. We will not spend too much of time on this, but we still want to see the impact of these optimizations on the given code. So, let us examine a copy propagation and dead code elimination. Observe here that we have x is equal to T3 and there is a T4 is equal to x. Similarly, here x is equal to T3 and a T1 is equal to x, which means that here we can actually replace this x by T3, because x is nothing but a copy of T3 and we can propagate that copy wherever x is being used, right. So, that is called copy propagation. So, we do copy propagation and we change it this way. What is the advantage of that? Can someone tell me what is the advantage of that? I did not reduce the number of computations at all. So, what is the fun in doing this? Beg your pardon? Reducing the memory, okay, reducing the number of variables and thereby reducing, that is one way of looking at it. Any other possible advantage? Any guesses? But x and T3 were copies of each other. How does it matter whether you use x or T3? Okay, let us look at the question slightly differently. We have now replaced this x by T3. What do we do with this x? What do we use this x for? Nothing is not required. This assignment to x now becomes redundant, right. We are storing value in x and x is not being used, just because that is dead code elimination. So, copy propagation leads to dead code elimination, and what typically happens is one optimization often leads to other optimizations, and there is no known fixed sequence of optimizations that we can perform. In fact, this problem is undecidable. You cannot find out a fixed sequence of optimizations which will give you an optimal result. So, there is no way you can figure it out. So, what people do is, and what typical compilers do is, based on the experience they observe, based on the empirical data, they say let me do this optimization first, let me do that optimization first, but there is no guarantee of optimal code anyway. It is possible that you may still have one optimization leading to the other optimization which has not been done by a compiler, right. Okay, so that is copy propagation and dead code elimination. Let us look at the final optimization, strength reduction and induction variable elimination. Observe here that we have j is equal to j minus 1, and whenever where is the increment, yeah, where we have j is equal to j minus 1 and we have T4 is equal to 4 star j. So, whenever j decrements by 1, T4 decrements by 4, right. Similarly, whenever I increments by 1, T4 increments by 4, that is guaranteed. What that means is, whenever whatever we are doing here, this comparison between I and j could as well be done between T2 and T4, because the values move in a lockstep fashion. The Boolean condition, the values of j and T4, I and T2 are different, yes, but the comparison between the values smaller or greater, that comparison does not change, because the values are changing linearly, right. So, therefore, we can replace this by the temporary variables T4 and T2. Similarly, here we can simply write T2 is equal to T2 plus 4, and here we could write T4 is equal to T4 minus 4. The advantage of doing that is we are replacing a multiplication by an addition. An adder unit on an architecture is cheaper, there are more adder units than a multiplier units. and sometimes multiplication has a longer cycle length than addition. So, it is useful to replace multiplications by additions wherever possible. So, that is called strength reduction, and this is done typically in for computations within a loop, right. But if we have to replace this T2 is equal to T2 plus 4, we have to put an initial value in T2, we have to initialize T2 with something else, and that initialization has to happen outside of the loop. So, we can replace, we can do this initialization outside of the loop and replace this computation, and now the value of I from the loop has been eliminated. It is called induction variable elimination. So, this is strength reduction and induction variable elimination. So, you can see this code, original code, now there are lots of blank slots within these codes. Lots of statements have been eliminated, and lots of these statements have been eliminated within a loop, and in particular in a doubly nested loop. So, you have combinatorially large benefits of eliminating these optimization, right. So, this is the advantage of performing such an optimization, and program analysis grew out of the need of doing such a thing, right. So, optimizations are transformations based on some information, and systematic analysis is required for deriving the information, and we looked at data flow optimizations, and many control flow optimizations can also be performed. So, that is the summary of what we have done so far. So, before we go further, any questions? I want to make sure that we are all on the same page. Okay. So, now, so there are lots of analyses and optimizations, lots of categories of analysis and optimizations. So, there are some of them are machine dependent, some are independent, some of them are machine dependent. For example, instruction scheduling, register allocation, peephole optimizations, vectorizations, all these are machine dependent. If you want to know more about vectorization, for example, you could talk to Samira. Samira had taught you last week. So, she is doing a lot of work in vectorization, you could ask her questions about it. We are going to focus on this particular aspect, data flow analysis, which are basically we do not worry too much about machine architecture, we worry about the program and a program in its intermediate form, right. Okay. So, what is program analysis? Program analysis is deriving information about a given program, representing the dynamic behavior of the program. This is important. Program analysis does not amount to counting number of lines in a program, it is a static information, it is not a dynamic information. Program analysis does not say how many variables have been used. Program analysis is interested in almost always finding out something about the dynamic behavior, runtime of the program. Okay. And the interesting thing is, this is most often obtained without executing the program, and this is what makes it interesting. I want to know about runtime behavior of the program without running the program. I want to be able to predict what my program could be doing without actually having to execute the program, and that is what makes this field very interesting and very exciting. The most important requirement of this analysis is that, and in particular of static analysis, there is dynamic analysis as well, dynamic program analysis as well, but I belong to a different school of thought which essentially says do not put off until runtime what you can do at compile time. So, therefore, I do static analysis rather than dynamic analysis. So, when we talk about static analysis, it must represent all execution instances of a program. It cannot say that sometime in some run the program does this. We have to have a generic information which says that it represents every possible behavior in a conservative or approximate way. Okay. So, why is it useful? So, here are the applications. This is essentially a sales slide, why I am important, is that kind of a thing. So, we will not spend too much of time on it. It is useful because we can optimize the program, we can improve its time requirements, space requirements. energy requirements or power efficiency requirements. You do not want to charge your mobile every 2 hours, you would rather want it to hold its charge for a long time, and for that program optimization is very important. And a simple trick of program optimization is to analyze the program and figure out how many bit flips are happening in the memory. Every time a bit goes from 1 to 0, you are consuming some power, you are consuming some energy. So, can we reduce that? So, that allows us to change the programs, improve the efficiency of the programs, so that you do not have to charge your mobile very frequently, or your mobile does not heat up. We also want to good power efficiency. When you are holding a mobile in your hand, you do not want it to heat up just because it is executing a program. And compilation for special architectures, for example, multi-core, and a very important application of program analysis is verification and validation. How do we know program is doing what it is supposed to be doing? So, how can we provide guarantees such as the program will never divide a number by 0, never dereference a null pointer, it will close all open files, it will close all open socket connections, it will not allow buffer overflow security violation. How can we guarantee? I mean, now in this era, security is becoming, software security is becoming very important, and there are many attacks such as SQL injection attacks. How can we guarantee that there is SQL injection attack in this program is not possible? So, these are the kind of things which require program analysis. And finally, there are many software engineering issues, maintenance, upgradation, enhancements, etc., for which program analysis is useful, right. So, having looked at an overview of classical optimizations and motivated the need of program analysis, let us now look at a contemporary optimization, optimization of modern era. These were all old optimizations invented way back maybe 40 years ago, 45 years ago in 60s and 70s. So, let us talk about modern optimizations, so which is optimizing heap memory usage. What time do we have the tea break? What is roughly the schedule that we follow? 11 o'clock. Okay, so we have time. Okay, so here is the shared memory architecture of the programs. Typical memory is divided like this. This is a logical division. So, there is a code memory. Some part of the memory holds the code. Some part of the memory holds the static data, and then we have stack and heap. And stack and heap keep changing at runtime, right, and therefore, they are typically allowed to grow towards each other. We are interested in talking about the heap memory, which is different from, which behave, although both the memories keep changing, the sizes keep changing, the behavior is subtly different at runtime. And how is it different? Heap memory allows creation of data structure whose sizes can change at runtime. You can't have such a facility on a stack. When you declare something on stack, its size remains fixed, you cannot change it. So, variable sizes is one big advantage of heap memory. The second big advantage of heap memory is that the lifetime of the data can outlive the procedure that creates it. When you allocate a data on stack, some piece of data on stack, that it is gone once the procedure invocation is over, whereas heap memory says that you create data and the procedure is the execution of the procedure is over, but the data can reside in the memory. So, variable lifetime and variable size is a big advantage of using heap memory over stack memory. Okay. And with that, two important questions that have to be answered: when do we allocate heap memory and when do we deallocate heap memory? In case of stack memory, these questions are implicit. Memory is allocated as soon as function invocation begins, memory is deallocated when the function invocation is over. In case of heap memory, allocation is very easy. Whenever there is a need, either the programmer makes an explicit request, please give me a memory chunk of 48 bytes, or you introduce some operation which requires additional memory. So, this is something specified in the program. So, this is not really an interesting question. The real interesting question is when to deallocate. How do I know that I am done with this heap memory, right? If I am done with this heap memory, I would like to deallocate it so that it can be reused for something else, right. So, when we talk about manual deallocation, so one way is manual deallocation, we write in the program free this chunk of memory, or we say delete this object or some such thing, but we all know from experience that this is really not a very good method, in the sense that programmers forget to deallocate memory. In fact, if you have friends and acquaintances in the industry, they would tell you that memory leaks is an industrial reality. What is a memory leak? You allocate a memory and never reclaim it, and the program continues to run again and again. I mean, not again and again, in the same execution instance of a program. There are programs, for example, operating system, or there are programs, for example, the one that controls lifts in the building, they continue to run. You do not rerun a program. So, these are transactional programs that continue to run for a long time, and when memory leaks occur in these programs, when you allocate a memory and do not deallocate it, it keeps asking for more and more memory until a time when it runs out of memory. So, memory has leaked away, and that plugging that memory leak is an industrial reality, and I am told that last 10 to 15% of effort goes in plugging these memory leaks, manually identifying where memory leak is happening. As against this, there is this automatic deallocation, also called garbage collection. You would have done, if you done a programming languages course, you would have come across these terms, two terms which you would have learnt by heart, and your university exam will ask you the definitions: garbage and dangling pointer, and everyone will immediately say dangling pointer is a pointer that does not point to a valid memory, and garbage is a memory which has been allocated, does not have a pointer pointing to it, right. We all know that definition. So, we are talking about that garbage collection. So, what garbage collection says is that if you have a memory location which is not reachable from, which is not accessible from a program variable, then that is something that is unusable, it is provably unusable, and therefore, we can reclaim that. So, this is, so the idea is to retain active data structure and deallocate active data structure, and the question is, what is an active data structure? So, if an object does not have an access path, that is, it is unreachable, its memory can be reclaimed, which is obviously the case, but this definition leaves something outside of the scope of the garbage collection. For example, what happens if an object has an access path, but is not accessed after a given program point? It is also possible that a memory object is reachable from a program variable, but a program does not need that object after that program point. For example, if you are writing a compiler, you have a symbol table and there is a type information in the symbol table, there is some other information in the symbol table. After you have done all your analysis and assigned offsets, etc., type information is perhaps not required by the backend, but the type information part of the table, symbol table, is reachable, but it is not required. That is also garbage, but textbook definition does not identify it as a garbage. Let us look at a concrete example. So, we are using Java style statements for convenience. So, we have this program where we have variables on the stack, and this is the heap memory, and for simplicity I have not taken stack directed pointers that would appear in C and C++, but this is a simplistic simplifying assumption, does not change anything that we are doing. So, here we are looking at this program, and this is how the memory looks at this program point. W and X have been assigned, and we have some condition based on which this X pointer moves rightwards, and if we go by the standard textbook definition, the only garbage nodes are P and Q, right, because every other node memory object is reachable from a program variable. Okay, so,